Hello, guys. Happy week 4 or lesson 4 of statistics. So this week we are moving on to Salkind chapter 4, which is on visual representations of data. If you have not yet done so before watching this video, I encourage you to read Salkind chapter 4. It will help this lesson go more smoothly. A kind of a quick look ahead at what we have coming up next. Good news is that after this week's lesson on chapter 4, we are done with new material until after the midterm exam. So next week you'll have all week to work on project number 1 that requires you to tie some things together from the first 4 chapters that we've done so far. And then the week after that, you have the entire week to work on the midterm exam, which assesses your ability to do things by hand. So that's what we have coming up for the next couple of weeks. So after this lesson, good news is you don't have new material for a while. So let me go ahead and get started. Oh, there's the babies, not what I wanted. The crumb snatchers. Okay, so let's do Chapter 4, visual representations of data. Remember, if you haven't already done so, I encourage you also to make sure that you have the lesson handout printed out, or at least up on the computer to help you be taking notes during this lesson. This is one that we're not doing a ton of stuff by hand, just one thing in the beginning, so that if you don't have the lesson handout printed out, it's not as big of a deal as if when we were doing like standard deviation, etc. Okay, I'm going to turn my video off actually. All right, so chapter 4, let's get rolling. All right, so there's a couple of ways we'll talk about of illustrating data, and all of the numeric ways to summarize a distribution are helpful, right? We've talked about measures of central tendency and measures of variability, but sometimes a visual may be most effective. Excel, as we'll see, I'll have a second part of this lesson where we do everything in Excel, but Excel calls these charts. All right, the first one is the most challenging. So we're going to get this one just out of the way at the start. This one way to visualize data is to use what's called a frequency distribution. And this essentially is a tally or summing of how often certain scores occur in a data set. So it groups scores into what's called a class interval, which is essentially just a range of numbers. So if we look first on this example I have on the right here, it's possible I give you this data set, right? That let's say these are, I don't know, meal prices, right? So the dollar menu at McDonald's up to a fancy $33 seafood platter. So these are a set of 15 different meal prices, and we want to kind of create a visual representation of how often some of these values occur within certain ranges, right? And so what a frequency distribution looks like is here on the bottom. So you have in a frequency distribution 2 columns. One column is called class intervals. Think about this as just range of values. And then your second column is called frequencies. Frequencies are the number of times each value occurs in a data set. So think of frequencies as frequently, or if it helps you remember what it means, how frequently do those values appear in the data set. So I have here class intervals that range from 0 to 4, 5 to 9, 10 to 14. And so this 0 to 4 has a frequency of 3. Where does that come from? There's 3 values in our data set that are between 0 and 4, right? 1, 2, 3 in the data set. The 1, 3, and 3 are the 3 values that are between 0 and 4. How many values are between 5 and 9? Is 1, 2, 3. How many values are between 10 and 14? Here, there's just 1, right? So I hope that you get the idea of that. But the idea of a frequency distribution is just that you have these range of values in one column, and then the number of times that those values appear, how frequently they appear, called the frequencies, in the other column. So when you're creating a frequency distribution, how do you know how big or wide to make each of these class intervals or ranges? And I have listed here some guidelines for defining how large each interval should be. And again, this is one of these, just like the statistics gods have determined, this is how it should be. So that normally there should be a range of 2, 5, 10, 15, or 20 data points. 5 to 20 intervals could cover the entire range of data, right? So this is 1, 2, 3, 4, 5, 6, 7. Anything you shouldn't, for example, create a frequency distribution with just 3 rows with 3 class intervals, right? So if I gave you this data set and said, you know, make me a frequency distribution, don't do like 0 to 15 and 16 to 30 and just have 2 rows. That's not very helpful in terms of looking at how spread out the values are, right? So when I say the range should be between 5 and 20 intervals, you should have 5 to 20 different rows of values here. And we'll look at why that matters in a minute. But think to yourself first, obviously that's kind of like a cheating, like I'm not going to create a class interval for these data that are just like 0 to 35, right? And you write the number of frequencies for 0 to 35 is 15, right? That you put all of the values in one bucket in one range. A kind of helpful way to think about, if we know we want 5 to 20 rows, one way to do it is to compute the range for the data that are given, then divide by the number of intervals you want to use, knowing that you want to use between 5 and 20, so that the highest, so that you avoid having to, when doing this by hand, like fill in the rows as you get to the top. And you'll see what I mean by that in a minute. But when I say to compute the range, then divide by the number of intervals you want to use, perhaps for this one, we know we want to use around 6 or around 7 intervals, meaning around 6 or 7 different rows. If we compute the range, remember the formula for range is the highest value minus the lowest value. So 33 minus 1 would be 32. And if we have our range of 32, then we can divide by the number of values, or number of intervals we want, the number of rows we want, which let's say we think like 6 would be a good number. We divide 32 by 6, and that gives us range of 5.3. So that gives us some guidelines on how big each class interval should be. And you'll see why this matters in a minute, but the last point here, the last guideline, is that the highest interval always goes at the top, that the lowest class interval goes at the bottom. So always, when you have a frequency distribution, you have a lot of flexibility in creating it how you want. But the few things that I look for in terms of making sure that it's done correctly are that you have these columns set up with class intervals and frequencies, that the intervals that you create are not too big, right? That they shouldn't be something that's like encompassing all of the data, and that your frequency counts are correct, right? You've appropriately counted up how many values, for example, are between 30 and 34. And the other key thing is that you have then the lowest values at the bottom, the highest values at the top. So that's what I'll look for when assessing your frequency distributions. Let's do one together, and I think this will make a little more sense. So this part at the top here about completing the frequency part, we're counting up the number of times a score occurs. So let's say I give you these data here. So this is kind of a bigger data set ranging from 1 to 30. Let's say these are also meal prices, right? And we want to create a frequency distribution for these 30 meal prices. How do we go about, how do we start creating that? I mentioned before that it can be helpful if we're asking ourselves, okay, how do I even start setting up my table, right? My 2 columns for class intervals and frequencies. How do I know how many rows I should I should create and how big should each of those ranges be. So let's say looking at this, I know that I want 10 intervals, right? This is a kind of larger data set with 30 values. 10 intervals or 10 rows would be appropriate. So first I calculate the range, where range is our high value minus our low value. Our highest value here is 30. Our lowest value is 1. 30 minus 1 is 29. And I know that I want about 10 intervals. So I do 29 divided by 10 and get 2.9. Obviously, you're not going to do a range of 0 to 2.9, 3 to 5.9 or whatever, right? But rather, this is just giving you some guidance on how big, if you know you want 10 rows, how big each range should be. Otherwise, you could start this process and say, okay, I'm going to do like 0 to 2 and 3 to 5 and start building it up from the bottom and realize all of a sudden, oh my gosh, I have 25 rows and that's way more than I wanted. So the goal here is to be thinking about what is a way that we can organize the data effectively without having too many rows. So 3 kind of gives us a sense of the interval range. I should also emphasize that, and this was clear in this one, but that your class intervals always need to be equal, right? That there needs to be the same number of values in each. I apologize, I should have emphasized that more when looking at this first one, right? Because here, so we have, remember, 0 counts as a value. So if you're going to include 0, make sure that you count that as a value. 0 to 4, that's 5 different values. 5 to 9, that's 5 different values, right? It's inclusive of the 5 and the 9. 10 to 14 is 5 different values. 10, 11, 12, 13, 14. Same thing for the other ones, right? So that the ranges need to be exactly equal for each class interval. Okay, so let's get started on this one. We first set this up by creating our chart, where you have one column with the class intervals, one column with the frequencies. Start at the bottom, and if you know we're going to start with 10, our goal is to have 10 rows, it's going to give us approximately 10 if we're rounding here, right? I think this one ends up as 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, but we're close to that 10, right? By doing this, this is giving us a sense of a ballpark estimate, right? It doesn't need to be perfect, the number of rows that you want, but this is giving us a ballpark estimate. And we determined here with it giving us doing a interval range of 3 is going to get us close to that 10, that 10 rows. So here we have 0 to 2, that's 3 values, right? 0, 1, 2 is 3 values. 3 to 5 is 3 values, 3, 4, 5. And then you just do the same thing all the way up, right? That we're creating ranges of values that are 3 values at a time. Then the next step is to look at your data and count up, okay, how many times does a 0, 1, or a 2 appear? And we look at that and see that there's 1 time, right? In the data up here, 1 only appears once. Then we look at our data and say, how many times does a 3, 4, or a 5 appear? Here, those appear twice. There's 2 5s. How many times does a 6, 7, or 8 appear? Here there's 0, right? We have 0, 6, 7, or 8s. How many times does a 9, 10, or 11 appear? That happens 3 times. And go all the way up, right? So you're tallying or counting up the number of times each value appears within each range of values, i.e. within your class intervals. Okay. And here's why frequency distributions are so important, because they are also a way to be able to chart data that becomes absolutely critical for doing more advanced statistics. And so if the way that we do this is using a frequency distribution, we can create a visual representation that's called a histogram. So a histogram essentially charts the frequencies of a frequency distribution. It might be helpful if you have your textbook to be following along in the text for this on pages 64 and 65, But as you set up your histogram, a histogram, and I won't normally make you do too many histograms by hand because I know it can be a tedious process, but it's really important for you to be able to understand how a frequency distribution leads into this visual representation of a histogram and the polygon that comes after it in a minute. So to do the histogram, your class intervals go along the bottom, right? These are the ranges of values from a frequency distribution. And then your frequencies go along the y-axis, right? Along the vertical line on the side here. Those are your frequency counts. And then you can essentially fill in, you're creating what looks like a bar chart for each part of the frequency distribution. So here, if we had a frequency distribution where our class interval was 0 to 4, there would be one value that happened 0 to 4. Then if 5 to 9 was the next range, there were two values that fell in 5 to 9. 10 to 14 is the next class interval, and that happened 4 times. 15 to 19 is the next range or class interval, and there were 8 of those values, et cetera, right? So that the idea here is that I just want you to be able to see how the frequency distribution leads into this visual representation of the data. And if we were live in person in class now, I would have you be doing this on graph paper so that you really processed how this works. What I care about at this point is that you can create a frequency distribution and you understand conceptually how that can turn into a histogram. I care less about your ability to do the kind of really nitpicky charting it out on graph paper by yourself, right? But I want you to understand conceptually when we see these visual representations of data, what that's representing, where that comes from. And so we're kind of moving in different stages here. We can start with our frequency distribution and see how a frequency distribution turns into a histogram, which is what we just did. And then we can also turn a histogram into what's called a frequency polygon. And a frequency polygon uses a continuous line that represents a distribution, right? So if we took the midpoint of each of these bars in our histogram and connected those with lines, this creates a visual representation of the data, right? So that if we know there's only one value on the low end that's between 0 and 4, compared to there's a lot of values up high here in the middle range, and only a few values down here at the higher range, this line here, this curve, is giving us a visual representation of that. So while a histogram uses these just vertical and horizontal lines that looks like a bar chart, the frequency polygon uses these curved lines to give a visual representation of what a data set looks like. And so when it's shaped like this, we'll have lots more on this later. Essentially, a lot of what we do after the midterm exam is based off of this shape that's called a normal distribution or a bell curve. And I'll say something more about that in a minute also. But so to kind of recap so far, we can look at a data set, a set of interval level data, turn those interval level data into a frequency distribution by tallying the number of times values occur within a certain range. Then we can use that frequency distribution to create a histogram, essentially a bar chart of the different values from your frequency distribution. Then that histogram can turn into a frequency polygon that uses these curved lines to represent the data. Okay, that's what the big parts that I want you to come away from from this first part of the lesson. Ways distributions can differ then. So looking at frequency polygons, looking at these curves, what are some ways that we can look at these and have understanding about the data set without even seeing the actual numbers? One thing that comparing these curves can do is we can see that different distributions have different averages, have different means. So they may have a different average value or measure of central tendency. Some distributions could have higher or lower average values than others. Let's pretend that I have, these are mean test scores for 3 different classes. This class meets at 8 a.m. This class on the left meets at 8 a.m. This class in the middle meets at noon, and this class on the right meets at 3 p.m. The 8 a.m. class has the lowest mean, right? The mean is the value that's in the middle. This class, the 8 a.m. class, has the lowest mean. The noon class has a higher mean than the 8 a.m. class, but the 3 p.m. class, that's the really high performing class that their mean is higher than the other 2 classes, right? And even looking at the lowest value, this would represent the lowest score for the 3 p.m. class. Even that lowest score is close to the mean for the noon class, right? So all of that I want you to be able to see for this is that having a frequency polygon for multiple different distributions, in this example for 3 different class periods, can help us illustrate if there's a different mean between different distributions, between different classes for this example. So frequency polygons can show different averages. They can also show different variability or how spread out a distribution is. So remember, a distribution is just a set of data, a set of values. And so some distributions may have the same mean, the same average value, but more or less variability. So perhaps we have, we'll continue with the same example of different class times, right? So distribution A is the 8 a.m. class. And the 8 a.m. class, everybody is pretty much close to the mean, right? So if we're looking at this one here for distribution A, we see everyone is pretty smushed in close to the mean, right? There's not that many, and this is, remember, thinking about how a frequency distribution turns into a histogram. That means there's not that many people who have a really low score, and there's not that many people who have a really high score. Most of them are smushed in here close to the mean, close to the average. Distribution B is a little more spread out, right? That there's still a good number of people that are close to the mean, not the same high number of people who are close to the mean, but there's still a good number of people in distribution B. This is, let's say, the noon class or whatever, that are close to the mean. But it's a little more spread out, right? There's more people here who have a low score. There's more people here who have a high score compared to distribution A. But distribution C, this one has the greatest spread, the greatest variability, right? This one, there's the lowest number of values right at the mean, and there's still a good number of people who have lower end scores and a good number of people who have higher end scores. In other words, they're more spread out, so that and if it's helpful for you to think about this in terms of visually looking at the data, that for both of these, perhaps for all 3 of these, class A, B, and C, the mean, the average is 50, but some are more spread out than others. Just looking at this visually, class A, sure, there's one person that has a 20 as a low score. There's one person that has a higher score as an 80 for distribution A, but most people are really smushed in here close to 50, close to the mean. Compared to class B, that's a little more spread out, right? People are farther away here from the mean. And class C, now this one is really spread out, right? That there's greater variability, that people are more spread out from the average. Okay, so another way that we can use frequency polygons is to be comparing different distributions in terms of variability. We can also look at what's called the skew of a frequency polygon. And skew is a measure of the lack of symmetry or lopsidedness of a distribution, right? So it's not always that the mean is right in the middle here, right? That the average is right in the middle. It doesn't always look like that perfect bell curve, but rather a frequency polygon can have values that are more lumped on one side or the other side. And if you read the chapter for today, I hope that you did. The chapter also gives formulas for calculating skew and calculating the next thing we'll look at, kurtosis. I think that's not necessary. It's beyond the scope of what we need to do in the class, so don't worry about that. I want you to just be able to visually look at and understand what skew looks like and what it means, right? So a skew is a distribution that's skewed, has one tail that's longer than the other, meaning that there's more values, there's a higher number of people at one end of the distribution, like the low end, or at the other end of the distribution, like the high end. So this one, anytime there's a distribution that has more data points, that the frequencies are greater to the left at the lower values, and then a long tail to the right, fewer people at the high scores, that's called a positive skew. So a positive skew is when there's more low values and only a few high values. A negative skew is when there's a lot of data points to the right and not that many to the left, so that there's a higher number of people or cases with high values and not that many with low values. So when the big lump or hump is to the left, that's a positive skew. When the big hump or lump is to the right, that's a negative skew. I'll share with you, this has always been the way that I remember which is positive and which is negative. When I was in graduate school, I had a statistics professor who was kind of an old curmudgeon, and he said to us, the way to remember this is when you become a teacher, it's a bad thing, it's negative to have a class where there's a lot of high scores. As a professor, you don't want to have a lot of high scores. That means you're not being tough enough. Obviously, that's not the way that I conceptualize my role in teaching, but it's always helped me remember, so that as a teacher, it's negative, it's a bad thing to have lots of high scores. It's a good thing to have lots of low scores because that means you're being tough. Again, this was his message, this old curmudgeon, on how to remember this. Not the way I teach, but if that's a helpful, thing to help you remember which way is positive and which is negative, feel free to use that. So negative skew is more values at the high end. Positive skew, more values at the low end. Okay, another way that looking at the frequency polygons can be helpful is kurtosis. So kurtosis is a measure that relates to variability. It relates to how flat or peaked a distribution appears. So while skew looks at where do values lump together in terms of being low or high, kurtosis looks at how spread out our values. It looks at how dispersed or variable a distribution is. And there's three different terms here for these. One option is for what's called platykurtic, to have kurtosis that is platykurtic. This is when a distribution that's relatively flat compared to a normal bell curve, right? So this one that's really spread out here, that's flat, this is called platykurtic. So compared to the bell curve, compared to this normal curve, this one is more spread out, so that's called platykurtic. Mnemonic device for this, think plateau. Plateau is something that's flat, or I always think of platypus. A platypus's tail is really flat, right? So if that helps you remember, feel free to use it. So platykurtic is this flat one that shows a distribution that's really spread out, right? That there's a good number of high values, there's a lot of values in the middle, there's a good number of low values. Compared to what's called leptokurtic, so this one with a really high peak, this one has not too many people with high scores, not too many people with low scores, but a whole lot of people with scores in the middle, right? So that creates this high peak. If there's a high peak that's that's called leptokurtic. So compared to the bell curve, right, compared to the perfectly even bell curve, one that peaks high in the middle is called leptokurtic. Then the name for kurtosis related to the normal or bell-shaped distribution is called mesokurtic. So this one is distribution B that has no kurtosis is also called mesokurtic. So the really flat one that's very spread out, platykurtic. The really peaked one that's doesn't have a lot of dispersion, doesn't have a lot of variability is called leptokurtic. And then the bell curve one, the normal is mesokurtic. This next part here, this is really the basis of almost everything that we're going to work on after the midterm, but because it kind of fits in here, I'm just planting this seed in your brain at this point. So this is, don't freak out if this looks overwhelming and there's not too much that you understand about it at this point, but I want to be kind of making this connection, starting to connect these brain cells at this point, because we're talking about normal curves and the bell-shaped and this idea, introducing the idea of the frequency polygon. I think in my experience with students is that it's helpful to kind of mention this, start getting this in your brain now, and then we'll really unpack it after the midterm. But there's a couple of characteristics of normal curves. So how do we know that something is a bell curve or a normal curve when we're looking at frequency polygons? First, they are perfectly symmetric around their mean, right? So that if the mean is in the middle, each side is totally the same, right? There's the same number of values and the same distribution or spread of values to the left on the low end as there is to the right on the high end. So they're perfectly symmetrical. They're a mirror image of itself around the mean. The other characteristic of normal curves is that the mean, median, and mode are all equal, so that there are not outliers that would make the mean and the median different, but the mean, median, and mode are all the same in the middle. Then this next part is really the basis of all inferential statistics that we look at, or what are called parametric statistics, next semester in 302, and that we start to introduce the concepts of after the midterm this semester. The reason that the normal curve is so important is because we know that there's always 68% of all values occur within just one standard deviation of the mean. So if we know the mean and we know the standard deviation for a distribution, we can say we know that all values, 68% of all values are within one standard deviation of the mean. 95% of all values are within two standard deviations of the mean, always, always, always with a normal curve. And nearly all values, 99% plus of all values, are within three standard deviations of the mean. So if, for example, we had a mean of 5 and a standard deviation of 1, I would be able to say that within one standard deviation, this would be with a mean of 5 and a standard deviation of 1, this would be 4 and this would be 6. I would be able to say, I know that 68% of all values are between 4 and 6. Again, I'm not going to be asking you to do the math on that now, but I'm introducing this concept as a seed in your brain because it helps make these connections when we start looking at this idea of the normal curve more after the midterm. So don't stress, I'm not asking you to do anything with the normal curve at this point. Again, it will be helpful if we start thinking about this now for when we look at it later. Okay, last chunk of this lesson then is on other ways to chart data. One way is called a column or a bar chart. Generally, a column chart is one in which the is just the reverse of a bar chart in terms of the axes. So instead of having the names of the categories along the bottom, for a column chart, you have the names of the categories over here, and the frequencies are along the bottom. A bar chart is when you have the names of the categories or groups along the bottom and the frequencies for which that category appears along the y-axis along the side. So we can use them interchangeably. We'll see when we look in Excel that you can pick between column or bar chart, and all it does is flip the direction of the bars, right? Do the bars go this way for a column chart, or do they go up and down like this for a bar chart? But we know that it's appropriate to use a column or a bar chart if we want to compare the frequencies of different categories with one another. So here what's important is that a column or a bar chart is used for a nominal or ordinal level variable, right? Or when the categories are nominal or ordinal, right? So that here, for example, I'm looking at the incarceration rate. Incarceration rate is an interval level variable, but we know that the interval level variable has categories, right? That the names of different countries for it. So anytime that we have names of different countries for our categories, then a bar or column chart is important. You should never be using a column or bar chart if the names of your categories are something numeric, because then that would really be a histogram. So the difference between a histogram and a column or bar chart is a histogram has numeric values along the bottom as your different categories, whereas for a column or bar chart, you're using named categories, right? So that this, I hope, illustrates that. So anytime we're comparing frequencies of different categories, then we use a column or a bar chart. A line chart is one that I want to introduce to you, but that we, this requires data that are set up a little differently than we usually look at, so we won't do much practice with this. But a line chart is used in which we're showing trends or change over time. So we have several data points that we're connecting with lines to be able to show trends. So the example I have here is this is actually a double line chart, right? That there's two sets of data being used, but the blue is the violent offense rate, right? This is the rate of violent crime. You can see here that the violent crime rate has been dropping since the 1990s. But so the violent crime rate, so we have a data point for 1960, for 1961, 62, 63, 64, 65, right, for each year. And then we use a line to connect each of those dots. That's what a line chart does. So a line chart is only appropriate if you have multiple data points that show change or trends over time. So you'll see in the classwork and the homework, I'll give some examples of different types of data sets, and I'll ask you to say, is it appropriate to use a bar chart or a line chart or a pie chart, with which we'll look at next. The terms that I have bolded on the slides here should be the key part you're thinking about. So for column or bar charts, if you're comparing frequencies of different categories, that's when you know to use a column or bar chart. If you're looking at change or trends over time, that's how you know when to use a line chart. And then finally, if you're comparing proportions of something, that's when you know to use a pie chart. So I have in the example here, prisoners and people incarcerated as of 2018, what is their main offense type? And so then the pie chart is showing the proportion of the entire prison population that's incarcerated for different types of offenses, right? And so that the pie chart is used for proportions. If it's helpful for you, make yourself a little cheat sheet that says something like bar and column chart is for comparing frequencies of different categories, line chart, change over time, pie chart, proportions of responses. All right, and that is it. So the next thing that you should be working on then is the classwork for chapter 4. So I hope that you feel good about this. If you have questions, send me an email, and I'm happy to set up a live class this week too if needed. All right, good luck, guys. I'll talk to you soon.